Okay, so we're going to go to y equals in your calculator. And sorry, give me 1 second. Okay, we're gonna let's read this problem here. A particle moves along the y-axis. So typically, if it's a particle motion problem, it's usually along the x-axis, moving left and right. Right is positive, left is negative velocity. Here is along the y-axis, so upwards is positive velocity. In this case, negative velocity would be going down. Velocity given by v of t, so this is our velocity function. In your calculator, you're always going to use x. Okay, don't try to use any other variable besides x. So we're going to adapt it and call it x sine x squared. So go ahead and type that in. Oh, and also one thing for this course is that we're always using radian mode. We're never using degree mode. So we want to make sure, especially if there's trig involved, that we are always in radian mode and not in degree mode. So if you click on mode, it's next to your second button there, and just make sure radian mode is the one that's highlighted. So x sine x squared. Now, part A says, in which direction is the particle moving at time t equals 1.5? So can we use velocity function for this? If we're trying to figure out the direction of motion? Yes, yeah. So if I plug 1.5 in for my position, my velocity function, if I get a positive, that means it's positive velocity. If it's negative, that means it's negative velocity. Now, to allow for us to plug this in without having to do it one at a time, if you can go to second mode, that'll take you back to your home screen. And I think most recalculators have this feature. I'm using an older one. Let me try again. X sine x squared. Okay, yeah. If you see that alpha, there's that button below second. If you go alpha y equals, alpha window, there's all, sorry, and then it's alpha trace. If you do alpha trace, here are a shortcut for you to call any of these functions here. So if you do alpha trace, you can get to y1. But go back to your home screen first. If you go to second mode, go back to your home screen, alpha trace will allow you to call that function. And then if I do parentheses 1.5, it's just going to plug in 1.5 in for all the x's of the function you defined previously. So again, under y1, you'll enter in x sine x squared, do second mode to get out into your back to your home screen, and then you'll do alpha trace to call your y1, and then once y1 shows up, you do y1 parentheses 1.5. And that's just going to tell us what the velocity is at that moment in time, since we plugged in v of t in for our y1. So my velocity is 1.167. which is greater than 0, and therefore my particle is moving up. Next up, find the acceleration. So acceleration is the what of velocity derivative. Now we could do this by hand. If we were doing this by hand, x sine or t sine t squared, what rule would you use to get to acceleration? Product rule. Product rule is a little bit of chain rule, but this is a calculator portion. We can make the calculator do it for us. So there's a derivative feature in your calculator where you can ask the calculator to find the derivative at a point. So if you do math 8, you can type in 8 or you can scroll down to 8, but you'll see that n deriv. Put it on the board here. This will allow you to find the derivative at a point. So you're going to just do d over dx. We're always finding the derivative with respect to x. And we want to put in our velocity function because we're going to ask the calculator to evaluate the derivative of velocity at 1.5. But rather than typing in x sine x squared, we already have that saved under y1. So if you do alpha trace y1, you can make the calculator just recall that velocity function for you. And if you type in 1.5, that will get you your velocity's derivative at that point, which is acceleration. Okay, so to finish off the problem, we can say that v prime of 1.5, or you can say acceleration at 1.5 equals negative 2.049. Negative 2.049 is less than 0. Negative acceleration means the slope of velocity is negative. If the slope of the velocity is negative, that means my velocity is decreasing. Part C. Given that y of t is the position function, we do know that velocity, v of t, is our velocity function, right? We're given that y of 0 is equal to 3. We're trying to find y of 2. So let's use first theorem to connect velocity and velocity and position, right? We know this is true. We know that the integral from a to b of v of t is going to end up being what? Velocity turns into position, right? And here they're using y as position, so we're going to use y. So it's just going to be y of what? How do we evaluate the bounds? Y of b minus y of a. Okay. So we know that this is our formula that we're using. We have our bounds 0 and 3, sorry, 0 and 2. So I'm just going to rewrite it using 0 and 2. And let's spell everything out, and then we can make our substitutions. So y of 0 we can replace with 3. Y of 2 is the unknown. And this, we can actually make our calculator also evaluate a definite integral for us. Okay, they can find the derivative at a point. They can also do a definite integral for us. So to do that, I'm going to go to Math 9. Or if you do math and scroll down to 9, you can do that as well. Or you can just type in 9. I'll leave this up on the board as well. Math 9 will get you your Fn integral. So most of your calculators have math print, so that's nice. It has the notations that you can expect. So we're just going to type everything in, right? So we want to find the accumulation of our velocity from 0 to 2. Again, we have our velocity function stored under y1, so do alpha trace y1, and then it's always with respect to x. So we know that from 0 to 2, our this displacement is 0.828. We know y of 0 is a certain value, and we can just work backwards and figure out what y of 2 is. I'm going to round that to 0.827. Okay, this leads us to part D. Any questions so far? So really what's new with our calculator that you haven't learned before are just these two notations. Math 8 will help you find the derivative at a point. Math 9 will help you find the depth integral. But all the other features are just graphing features that most of you guys, I think, know pretty well. So I want to make a distinction here for part D. If I just do the integral from a to b of v of t dt, this will give me simply displacement. This will tell me how far I am from where I started. Because if I accumulate velocity, it's going to add up all the positive and negative regions, right? So if I move to the right 4 units, then left 3 units, it's going to keep track and it's going to go back and forth. But if I put an absolute value around v of t, then this is going to give me total distance. So for instance, let's say I had a velocity graph that looked like this. For displacement, it's going to keep all these signs. You move 4 right, you move left 6 units, you move 5 units to the right. Where are you going to end up? That's what displacement will tell you. The total distance will tell you how far you're going to travel. So it's going to say, okay, I traveled 4 units, I took another 6 units, I took another 5 units. So your total distance will make all your negatives positive, and that's what this absolute value does. So 4 plus 6 plus 5 will be 15. So total distance will make all your negative regions positive. Right. So that's what part D is saying. Part D is saying find the total distance traveled from 0 to 2. So we're just going to say from 0 to 2, absolute value of v of t dt equals 2. So again, you're going to do math 9 to get to your definite integral. from 0 to 2. And now you're going to do math, number, ABS. That's going to get you your absolute value bars. I'll put down the board as well. And I'll leave these on the board for the test. Now your absolute value bar is only going to be around your velocity. Don't put it around the integral. Don't involve the dt. It's just simply around your velocity function. Okay. And then to get to your y1 that we have stored, you can do alpha trace y1. And then close it off with dx. It may take a little bit longer for it to calculate, but it will get there. Okay, did you guys get 1.173? So your distance and your displacement, if anything, your distance is usually a larger value than your displacement, assuming same interval and same function, because this is keeping track of your forwards and backwards. But if there is no distinction between displacement and total distance, that means this object never changed direction. That means it's only going right, or it's only either going always going up or always going down in that interval. But if there's any change in direction, then you can expect your total distance to be a larger value than your displacement. Any questions here? All right, so let's look at number 2. We have a table of values. The temperature in degrees Celsius of the water in pond in a differentiable function, W. So that just tells us that this whole graph is a smooth curve. Okay. And then on top of that, there's not going to be any sudden jumps or any values that's undefined. Every value is defined in between these integers. This table above shows the water temperature as recorded every 3 days over a 15-day period. So that means day 0, the temperature of the water is 20 degrees Celsius. Day 3, the temperature again, 31 degrees, drops down to 28, drops down to 24, continues dropping, 22 and 21. All right. Now, a lot of things can happen between these times, but these are the only limited. This is the limited data that we have to work from. Use the data from the table to approximate W prime of 12. So this is a derivative notation, but what's the algebra version of derivative? Slope, right? So basically, it's asking what is the rate of change, or what is the slope around 12? And all we need is what information do we need if we want to find slope? 2 points, right? So what 2 points could we choose? Yeah, 9 and 12. You can also make an argument for what? 12 and 15. And then there's also a third option. You could also make an argument for 9 and 15. But it's got to be circling around here, right? If you're using points that's further away, like 0 and 12, that's not accurate enough. You want to get as close to your source as possible if you want to improve your accuracy. So there's different variations of the answers that are all fine. I'm going to choose 12 and 15, but if you chose 9 and 12 and 9 and 15, those answers will be acceptable as well. So W prime of 12, we know this is not exact. We know this is just an approximated rate of change on the 12th day because we don't have calculus yet to help us get there. So it's change in temperature between 2 days divided by that time interval. Okay, so our units is change in temperature over the change in days. So degrees Celsius per day. So how can we phrase this? What does this mean?
The 12 days changing by.
Yeah, so on the 12th day, the temperature in the pond is decreasing or approximately decreasing at a rate of 1/3 degrees Celsius per day. Part D, approximate the average temperature. Average temperature here. What formula are we using there? Average what? Average value. Average value. So remind you, average value is 1 over b minus a, integral from a to b of f of x dx. That's the original formula. But for us, we're going to accumulate, it says using trapezoids. So let's do that. 1 over 15 minus 0, integral from 0 to 15 of w of t dt. Okay, so we're going to accumulate the area under the w of t function relying on trapezoids. So trapezoid formula is width over 2, or 1/2 width, height 1 plus height 2. Using all the subintervals given to us, so from middle of your order pair to the middle of your next order pair, those are your width. So all the widths are the same. And we're going to build out the trapezoid one by one. Okay, 1/2 width, height 1 plus height 2. We have 5 subintervals, so we should be able to create 5 areas of trapezoids. To save you time, that's just a bunch of entry into your calculator. That's going to end up giving us 376.5. Now we can go back to our average value theorem and make that substitution. So we accumulated all the temperatures divided by 15, and that should give us an average temperature. I mean, we see all these temperatures here between 20 and 31. So our average temperature should be some number between these numbers that we see, right? Like if we see our answer being 376, that doesn't quite feel right. It doesn't feel like average temperature if we're just oscillating between 20 and 30. So we got to divide by 15. And that's going to get us to 25.1 degrees. So part D says, or start part C, says a student proposes a function P as a model for the temperature of the water in pond T at time T. So now this function is supposedly going to give us a more accurate behavior in terms of the change in temperature over the course of it, not just at these 3-day increments. Now we have a model that can help us find the exact temperature or a better temperature approximation at any moment in time, not just 3-day intervals. So this is where calculus can come into play here. So here's our PFT function. PFT is measured in degrees Celsius, find P prime of 12. Now we can find the exact rate of change because we have a formula that we can find the derivative for. So for part C, we're just going to find P prime of 12. We're going to make the calculator do it for us. So here, I'll store this under Y2, but if you want to erase Y1 and type this in, you can. Again, what variable are we using for all of our functions in our calculator? Just X, yeah. So any variable that you see on paper, convert it to X. But on paper, you're going to leave it in the variable that is presented. Okay, so now math 8 will get you to your derivative feature. Alpha trace Y2 now, alpha trace Y2. And I want to evaluate my rate of change on the 12th day. So this should be related to part A. Part A is an approximated value. Part C is more accurate. They should be in the same ballpark of values, right? They're not the same, but we can kind of imagine that, okay, the approximation shouldn't be too far off from the exact rate of change. Part D. Now we can also find the average value without relying on trapezoid approximation. We can actually plug all this into our calculator. So over the 15-day interval, now you can use that math 9 feature. Alpha trace Y2. Don't forget to divide by 15. We want to find that average temperature. Should be pretty similar to part B, and it is 25.757 degrees Celsius. Okay, so in your, I do want to make sure I have time to go over complete the square and arc trig for your test tomorrow. So we'll pick up on Monday the rest of, but yeah, the rest of the problems that we want to go over. And we can kind of spread it out between Monday and Wednesday, even though we're covering new topics Tuesday and Wednesday in preparation for your Thursday test. Okay. If you guys can go to your test review packet, looks like this. Okay. Oh, good. Good. Thank you.
Thank you. Okay, you want me to get you the like those 2 pages for you tomorrow?
Yeah.
Okay,
Thank you.
I did.
All right. In your test review packet, the first page looks like this. Let's go to page 15. Number 7.
That's the one I did.
So you
That's the
did.
one I did. Yeah. Now it looks like I've worked.
Now, how do we know that, how do we know what category that this problem falls under?
You compare degrees.
Yeah, there's a gap in degrees, right? Degree 2 versus degree 0. So this is indicating, and there's no radicals. This is going to indicate for us a good fit for arc tangent, right? Arc trig. But we know that the denominator is not quite separated in that nice form, a squared plus u squared. So we do need to go through complete the square to help us get an expression, a variable expression that's squared, and the constant expression that's squared. So we're gonna, but ultimately we're targeting this formula here. So we're gonna step to the side here and just focus on trying to get that denominator to show us a different form, but we don't want to change the overall value. So whatever number we decide to add to allow this to factor nicely, we want to make sure we account for that number and subtract it immediately so we don't change the overall value of this expression. So what goes inside that space is b over 2 squared. What's our b value? 16. 16 over 2 is 8. 8 squared is 64. So this is going to factor nicely. Multiplies to be 64, adds it to be 16. It'll be 8 and 8. So now we can put it back into our problem here. We can combine that to be a binomial squared. Now this begins to look more like what we want with our tangent, but we know that anytime we want to assign our a and u value, we do want our denominator to show 2 sets of parentheses squared. The x plus 8 is ready to go. But what can I put inside this parentheses so that if I square it, I end up with 3. So now whatever is inside the parentheses are your a value and your u value. How can you tell the difference? You look to see what's the constant and what has a variable in. Your constant will be your a value. Whatever has your variable in it is your u value. Let's get everything in terms of a and u to get this to match exactly like the rule that we want to apply to convince ourselves that we're good to go. And then we can take our antiderivative from there. Yeah, you can. Yeah, if you have root 3 first, that's fine. Just make sure you're assigning your u and a value correctly. So if I pull the 7 out in front, dx gets replaced with du. I clearly have u squared plus a squared. And this is essentially the same as the rule that I want to apply. Once I cover up my coefficient, it should match exactly like the rule that I want to use. So now I'm ready to apply my rule. There's a 1 over a that's going to show up in front of my arctangent, but there's also a 7. So I need to make sure that both are showing up in front of my antiderivative. So 7 comes first, then the 1 over a. So 1 over what? Root 3. Arctangent of u over a. So u over a. Let's see. You don't have to rationalize your denominator. Radical in the denominator is fine. AP College Board as well. They won't care if you have radicals in the denominator. I just want to make sure I went over an arc trig problem that had complete the square, since you'll see it on the test tomorrow. If you can turn to page 16 in the same packet. This formula sheet here, I do want to highlight that there won't be any trig integrals involving natural log. We haven't gone over these. I'll probably go over this sometime this semester, but I'm not going to put it on the test. And then finally, page 20. Again, let me highlight what you can expect on the test tomorrow, non-calculator portion. So power rule integrals, know when to apply power rule. If there's only one term in the denominator, we can split up into individual fraction and largely rely on power rule. Use substitution, change your variable. Use substitution is your second option. If something cannot be handled using expansion, power rule, splitting up, then you can look at use substitution as your second option. Trig integrals, depth integrals involving unit circle values. We did that yesterday. It's also showed up in your homework yesterday, so make sure you review your integral rules for trig as well as your unit circle values. Depth integrals involving absolute value functions. So this is where we draw our absolute value function. It's going to just form two triangles, and you're just adding up the areas of the two triangles. Even and odd functions, we practiced those yesterday. Start with your shorter interval, then apply the even odd property on the other side of the y-axis, and then fill in the gaps with the larger interval. Second theorem of calculus, if I want to find the derivative of an integral, we have that rule f of p of x times p prime. But if both my bounds are variables, then I got to do f of p of x times p prime minus f of q of x times q prime. Average value theorem, we saw that today even in our calculator portion, 1 over b minus a, integral from a to b of f of x dx. Exponential integrals, a to the u du, e to the u du, make sure you know those rules. Natural log integrals, if I have a problem that looks like this, this has a certain look to it where we know this is going to be set up using synthetic division. And then we just did an arc trig to complete the square. Any questions about your test tomorrow? Okay, so be sure to look over your notes, be sure to look over your worksheets, be sure to look review over your derivative and integral rules. Okay. All right, come get your phones.